All right, good afternoon, everyone. Hope you had a good weekend. Looks like we're going to get back to business here. Oops. Hold on here. Does anyone have any questions before I start? We are covering 11.2, finishing 11.2 today, and then we're going to do 11.3. Hopefully, we should be able to get through that. We'll see. And then on Wednesday, we'll continue. And then Wednesday, I will be sending out the midterm, right? And you'll have, all the details will be on there about when it's due and everything else. So just expect that on Wednesday. It'll probably be right after class. I'll send it out. And then you'll have your spring break, right? So, all right. So no questions? All right. So last time we were talking about limits of functions of two variables. And basically the main conclusion that we came to was that in general, it's very hard to calculate the limit of a function of two variables because there's like this infinite number of paths that you would have to check. And so what we did instead is we looked at certain functions where we could show that the limit didn't exist at some point, which is easier to do because then you just have to show that the limit as you approach that point from two different paths gives you two different values. And in the homework problems I asked you to look at were of that type. But what I hadn't covered were problems where we could find the limit, and we can do that by applying the squeeze theorem. All right, now the squeeze theorem is something that you should have talked about in Cal 1. So I know it's been a long time. So I'm just going to kind of recap what that squeeze theorem was in Cal 1. The squeeze theorem in Cal 1 said basically, if you had, let me write this down for squeeze theorem. It said that if you have some function f of x, and that function is always smaller than some other function, I'll call it h of x, and always bigger than some other function g of x, then that means that when you graph those functions, the middle function, right, whatever it's doing, is always in between these two functions. So when you look at their graphs, the red one is always sandwiched in between the purple and the orange. And so if this is always true, then whenever you take the limit of this function, whatever that is, you say x approaches any number, doesn't matter. Whatever that limit is, the inequality must be true, that the limit of this one and the limit of this one maintain the inequality. So whatever the limit of h is, like let's just say, for example, we're approaching the value 2. It doesn't matter which value it is, but so if you take the limit of h as x approaches 2, whatever that answer is, it will be bigger than this limit. And then that limit will be bigger than or equal to this function's limit. And so what we have is the limit that you're looking for, which is the one in red, is somehow sandwiched between two. And what you're really hoping for is that these two go to the same number, okay? So those you want to be equal. Okay, if those two limits on each side are going to the same number, then that forces this one, squeezes it in between those two. So it has to be the same limit. So let me show you an example from Cal 1 of a problem that we would have used this for. So let's say we're trying to show that the limit as x approaches 0 of sine of x over x. Hold on, let me just think about this. Well, you know what? Let's go this way. X goes to infinity. Let's do that. Let's show that that equals 0. All right. So if we want to show that the limit as sine of x over x as x goes to infinity equals 0, what we could do is, well, you could use L'Hopital's rule, okay? But before you learn L'Hopital's rule, we learn the squeeze theorem. So unfortunately, we can't use L'Hopital with functions of two variables. So we're going to have to go back to squeeze theorem if we want to have any hope of doing this, all right? So the way we would do it is this. We would try and come up with some string of inequalities that we know is true. Okay, so basically we need this right here, we need that to be the middle function. And we just need to come up with two functions that create an upper and lower bound on this function. So the way you would do this is you would write this down first. We would write something we know, like for example, we know sine of x is bounded between -1 and 1. Sorry, I put the negative on the wrong side. We know this is true, right? Sine of x by itself has to be between -1 and 1 because that's the way we define sine, right? The range of sine is, you look at the sine curve, right? It's between -1 and 1. And then what we could do is we could divide everything by x. And if we do that, then we have the function we're looking at here, sine of x over x. We have that now squeezed in between two things. And now what we do is we take the limit, and let's approach infinity. Limit x approaches infinity of -1 over x. That must be less than or equal to the limit as x approaches infinity of sine x over x. But that must be less than or equal to the limit as x approaches infinity of 1 over x. And what you can see is that these two ends, these two limits go to the same value, right? They both go to 0. As x gets bigger, that fraction gets smaller. So this heads to 0. I should do it this way. This heads to 0. This heads to 0. And that means that we can conclude that that one must also head to 0. Right? Does that look somewhat familiar from Cal 1? Or does that logic make sense? Okay, so that's the squeeze theorem. Now we're looking at functions of two variables, and we're going to say, hey, we're going to use the squeeze theorem here, all right? So it's very similar to what I just put up here. We have some function. I'm going to put it here in red. Our function, this is what we're given, okay? We're given this. And what we need to do is come up with two other functions of x and y. So two other functions of two variables. And we need to squeeze the given function between these two. And then what we need to do is take the limit of this one, take the limit of this one, and hope, okay? We have to hope that they both go to the same number. And if they do, then we can say that that limit also goes to that number. And that's the only way we can do limits of functions of two variables without having, to look at all the paths, which is impossible for us to do anyway. Okay? So y'all ready to try one of these? Here we go. All right. So we want to find the limit as the point xy approaches 0, 0 of x squared sine squared y over x squared plus 2y squared. So this is the thing that we eventually need to squeeze, right? We need to come up with a way to squeeze this between two things. And it's up to us to determine what those two things are. And then we'll take the limit and hope we get that the two ends go to the same thing. So let's start with the left-hand side. Any guesses? I mean, we have to try something. Any guesses as to what this quantity should always be bigger than or equal to?
0.
0. Okay, that seems to make sense, right? Because look, x squared is positive. Sine of y could be negative, but then we're going to square it, right? So that should be positive. And then plus, let's see, x squared, that's positive, plus 2y squared, that's positive. So look, this thing has got to be positive. At the worst, it could be 0, right? But this would have to be greater than or equal to 0. So that seems like a reasonable guess. Good. Okay. Now, the good news is if we go now and we take the limit of the left side, the limit as any point approaches 0, 0, of that left side 0, well, that's just 0 because it's just a constant. So we know that that limit is approaching 0. So if this is going to work, then the function we pick here, we are going to need that limit also eventually goes to 0. If that's true, then we've got the squeeze. But we need to come up with the right side. So can anybody think of what? There's two things you have to think of here. Something that is bigger than this all the time, and you're going to be able to take the limit and let it go to, you're going to be able to take the limit and get the answer. But that's a problem, isn't it? Didn't we already say that taking a limit of a function of two variables is like impossible for us to do? Right? I mean, we can't check every path. So we can't do a limit of a function of two variables. We can do a limit of a function of one, but not two. So maybe what we choose here is a function that only has one variable in it. Is there any way we can think of something that's bigger than this, but only has x in it or only has y in it? Any ideas here? Let me take this down here for a moment. All right, so look, let me assist. Tell me about sine squared y. What's the biggest that could be?
1.
1. Everyone agree? Because you're going to take sine of y, which has to be between -1 and 1, and then you're going to square it, which still has to be, well, in that case, it would have to be between 0 and 1 because you're squaring it. So the worst case scenario, well, let's see, the smallest this could be would be 0, but the biggest it could be would be 1, right? So do you all agree with this inequality? Would this be true? This has to be smaller than or equal to x squared over x squared plus 2y squared. Do you all agree with that? In other words, I'm just replacing this with a 1 because that's the absolute biggest it could ever be, which means if I just put a 1 there instead, then this is bigger than or equal to anything that this could be equal to. Y'all agree with that? Okay, let's keep going. Is there anything you can say that's bigger than that? And try and get rid of one of the variables. Try and get rid of the x or the y. Is it tricky? Any ideas? Would you all agree that it's less than 1? That this is less than 1? Look at the numerator. The numerator is x squared, right? Look at the denominator. It's x squared plus a number, right? And this number 2y squared has to be positive. I mean, it could be 0, but it would have to add to the x squared. So it's like x squared over x squared, but then you add a little bit more on the bottom. This number down here must be bigger than that number, right? Which means that this ratio would have to be less than 1. So even though that's true, it doesn't help us. And the reason it doesn't help us is because if we were using the squeeze theorem, then we would have 0 on this side. We would put a 1 here. And if you take the limit as x, y approaches 0, 0 of 1, you get 1. Like nothing changes there. So you're basically saying that this limit is between 0 and 1, which doesn't squeeze anything. It does tell you it's between 0 and 1, but it doesn't tell you what it is. So for the squeeze theorem to work, we need this side to go to 0. All right, we need that to happen. So even though that's true, it's not going to help us. So anything else?
Could we put sine squared y?
Just sine squared y? Is that what you said?
Yeah.
Would that be true? What's your reasoning for that?
Because the biggest that sine squared y could be is 1.
So this could be, the biggest this could be would be 1, right? But I think, okay, so what you're saying is we could put this maybe, right? But I agree that that's less than or equal to 1. I agree with that, but that doesn't tell me about the relationship between these two. Like this could be less than 1, but this could also be less than 1, but there might be times where this is bigger than this one. So that may not.
So are we trying to get rid of the 2y squared?
Well, you're trying to come up with something over here that you know would be bigger than this. And that thing over here that we put must, when you take its limit, it must go to 0. So think about fractions. If you, whenever you have a fraction, let's just take a fraction like 5/7, right? If I, well, you know what, let me do it this way. 5/5 plus 3. Okay, think about that fraction right there, right?
It's 5/5 plus 5/3, right?
No, that's if it was the other way around. If it was 5, it was 5 plus 3 on top and 5 on the bottom, then you could split it up, but we can't here, right? This, I mean, if we just figure out what this is 5/8, right? Okay. Now, what I'm trying to get us to see, I guess, here is that we should all be comfortable with the idea that if you ever make a numerator, if you ever make the numerator of something bigger, the fraction gets bigger, right? And if you make the denominator of a fraction bigger without doing that, then the fraction gets smaller, doesn't it?
So we have to get rid of the x squares on both the numerator and the denominator.
Or would it be 1/x as a limit approaches?
Wait, say again?
Because I was gonna say if it's 1/x, because as the limit approaches, I was gonna say infinity. I don't know if it's approaching infinity.
Well,
Anyway,
the limit that we want in this problem is that x and y are both going to 0.
oh well, as the denominator is bigger, it'll be closer to 0, wouldn't it?
It would probably get closer to 0 faster than the numerator, yes. It would, but that still doesn't give us an algebraic expression. We need something algebraic over here that we can take the limit of. Let me write something down, okay? Let me write this down and see if, I'm not saying this is going to work or that it's even true. I'm just going to write it down and let's just see what you think about it. Okay, think about this. Now I'm going to put a question mark here. Not quite sure if that's true or not. But if it is true, okay, if that was true, then if I took the limit as x, y goes to 0, 0, then I would get 1/0, which basically becomes infinite, right? That's basically what would happen. I think that's, I don't know who said that a second ago, but I think that's kind of what they were saying. Yeah. So if we were to somehow show that this thing is bigger than or equal to this thing, then if we took the limit, it would give us infinity over here, which does not help us, right? It doesn't help us. Now, is that even true? And I said, is this true? Because what I was trying to do here is get this down to one variable. That's all I was trying to do is get it down to one variable. So this right here was an attempt to get it to one variable, but it doesn't work anyway. But how would I check if this is even true? I would just do this. This is a check. So what I would have to do to show this is true is like almost like a cross multiply. And x squared plus 2y squared, like that. And if you look at this, this is kind of inconclusive. There's not an easy way to show that this inequality is a true statement, right? So what am I getting at here? We are kind of in a tight spot here. We're still trying to come up with a way to squeeze this. And this is in general, the difficulty of these problems is trying to figure out the function to squeeze it with. So I'm just going to erase this and try something else.
Can you make your own 0 in the numerator?
How do you mean?
Like if you were to make the top x squared plus 2y squared minus 2y squared.
X squared plus, wait, say it again, x squared
Plus 2y
plus
squared
2y
minus
squared.
2.
Minus 2y squared,
Yeah,
and then split it up. Is that what you mean?
yeah.
Yeah, but if you split it, you'd still get the same expression. I think.
What
Are you
about x squared?
Hold on. Are you saying do x plus what? X squared?
No, x squared plus 2y squared minus 2y squared over x squared plus 2y squared.
Okay, so the suggestion here is if we were to rewrite this numerator as this, that would be true. And then put that over x squared plus 2y squared, right? Then you could split this into two things. You could split it into, I think you want me to split it here. Put this over this, right, which would be 1, minus, and now you have negative 2y squared, oops, sorry, plus, negative 2y squared over x squared plus y squared, like that. Is that what you were suggesting, maybe?
Yeah,
Okay, all right. Now,
maybe.
someone else said something?
What about x squared?
Just x squared by itself.
Yeah.
Well, that would be nice if x squared is bigger than this, then that would be nice, wouldn't it? Because then what's the limit of that? Take the limit as xy goes to 0, 0 of x squared. Well, x squared is just plug in 0 for x and you just get 0, right? And that would be exactly what we want. Can't be that easy though, is it? We would have to show that this is true. Is that true? Is x squared over x squared plus 2y squared less than x squared? Is x squared over x squared plus 2y squared smaller than just x squared?
Yes.
Yeah, it is actually. It is actually, right? Just all you have to do to convince yourself of this is divide both sides by x squared. Ooh. Divide both sides by x squared, or multiply both sides by 1 over x squared. How about that? And then these cancel and you get, this is a question, is this true, right? These cancel and I get 1 over x squared plus y squared, 2y squared. Well, hold on, is that true? I don't know. I'm having second thoughts. It's true if x is big, and it's true if y is big, right? Like if x is, let's say 1 and y is 1, then this thing is going to be like 1 divided by 3, which is, 1/3 is less than 1. But what if x is like 0.001 and y is like 0.001? Then if you put those together, that number is going to be smaller than 1, and therefore this ratio will be bigger than 1. So, man, that looked promising, didn't it? Because this would go where we want it to go, and the inequality almost looks like it works. Are there any questions why this is not true? Are there any questions why that's not true? No? Sure. If you wanted to, you could go one more step. You could take this and you could just multiply both sides by x squared plus 2y squared. If you do that, then I think that's obvious that that's true, right? Just multiply here and here by the denominator. There's no way. I can pick some x's right now where this will not hold, right? Okay, so I have intentionally led you down the wrong path. All right, I intentionally did that. right? But I wanted you to get a feel for how when you look at this a certain way, you can kind of get yourself stuck. And that's what makes these problems hard. All right, so I'm going to start over. I'm going to grab this again. And you'll probably find yourself doing this on the homework, trying to figure out like what in the world to use. So I'm going to start a new page. Now, we already know that this thing is bigger than or equal to 0. We're going to stick with that. But last time I said, hey, everyone, let's just convince ourselves that this right here, the biggest it can be is 1. And so we just rewrote everything and we replaced that with a 1, didn't we? And it didn't work. So now what I want you to do is focus your attention on this stuff. So in other words, we could write that as x squared over x squared plus 2y squared times sine squared y, right? That's another way we could write this. Now, what can you tell me about this? What is that always smaller than? If these two are the same, and I'm adding just a little bit here, then this fraction must always be what?
Maximum is 1.
The max is 1. Now, don't confuse what I just said with what we were doing a second ago. It didn't work here. Why didn't it work here? Because we canceled the x squareds and we had a 1 up here. 1 over this is not always less than or equal to 1. But if I have x squared over x squared plus 2y squared, and I'm asking myself, is that less than or equal to 1? The answer is yes, because I could multiply both sides by x squared plus 2y squared. And this is true, right? Just subtract x squared on both sides, you get 0 is less than or equal to 2y squared. And that will always be, this will always be true, right? That's always true. Pick any y you want. If I square it and multiply by 2, it's got to be positive. Worst case scenario, it's 0, but the inequality would be true then. So instead of putting over here on this side, replacing the sine squared y with 1, I'm going to say this must be less than or equal to the x squared over x squared plus 2y squared. That's going to be replaced with 1, which leaves me with just sine squared y. And now if it's down to one variable, and if we take the limit as x, y goes to 0, 0 of sine squared y, well, that's just a cal 1 limit, and you just replace y with 0, sine of 0, 0. So this is headed towards 0. And we know the left side's headed towards 0. And so we have squeezed it in between.
So you made the x squared over x squared plus 2y a 1?
I replaced it with a 1. If the biggest that stuff in green can be is 1, then sine squared times 1, right? Replace all that stuff with a 1, has to be bigger than or equal to this, right? Because the stuff in green has to be smaller than or equal to 1, which means this would have to be bigger than or equal to this. So there's no method I can give you that's going to be like, oh, when you see these, just do this. Like, you have to think through this, and you have to understand what's happening and what your goal is. What I can tell you that will be the case for all these problems is you've got to get something to squeeze to the same number. Okay, you've got to have the same number up from both sides, and the thing you pick on the right, whatever that is, you better be able to take the limit of it, which means it better be either a constant or it better be one variable in there. Because if it's 2 variables, you got to check every path, and you can't do that. Okay? So just see how it goes with your homework on those. Those are always a little bit of a head scratcher for most people. But
Do you suggest like maybe breaking up the numerator into how you did it, where it was you were multiplying 2 different things, and then like that you can see it easier?
yeah, I think if you go back now and you think about it, now that we've talked about it, it seems maybe natural now to try and make this part in yellow the thing that's going to be controlled by a single variable. So that means if you can look at the rest of it and somehow get control over it, like we did here, we got control over that piece, then that would seem like the path to go down. Yeah. Yeah. So have fun with those. They're not, you know, in the grand scheme of things, this is not a super important thing. I mean, I think it's important if you're a math major and you want to, you know, in math, if you're a math major, all you ever do is inequality stuff. I mean, it's all math ever becomes later is just a big old string of inequalities that you have to prove is true. So this sort of magical showing these strings of inequalities are true is just, it's just par for the course for math majors. Okay, going on. I believe that's it for that section. No, continuity. All right, yeah, there's one more thing. Okay, so remember, we talked about, first thing we did in this chapter is we said, hey, here's what a function of two variables is. They graph these surfaces. Then we talked about limits of those functions, because that's what we do in calculus, right? We start with functions from college algebra and pre-cal. We get to calculus, we talk about the limit of functions. So now we have this new type of function of several variables. We talked about its limit. Now the next thing in line is continuity. So when it comes to continuity, back from Cal 1, I'll write the definition up here so you have it. Back in Cal 1, if you had a function f of x, y equals f of x, the limit as x approaches a of f of x equals f of a, that's the definition of continuity. This is what it means to be continuous at a point x equals a. It just meant that as you approach a point, you're actually headed to the same value of the function. I'll give you a graphical illustration of this. So let's say we're going to some point a. To say that a function is continuous at a means that when you take the limit of the function as you approach a, that means the limit from the left and from the right, you're headed to the same place. Okay, so from the left side and from the right side of a, your function is headed to the same value. That's what it meant for the limit to exist. What's happening at a does not have any impact on the limit, not on the limit. But when it comes to continuity, you need this additional condition that not only is your function headed to the same place from both sides, it's actually headed to the function's value there, which means that dot must be filled in. Okay, that's what it means to be continuous. And so in Cal 1, you're taught that continuity basically means that you can draw the function without picking up your pencil. That's the basic idea of continuity, is that you can draw the function without picking up your pencil. So in functions of two variables, we have the same exact definition for continuity. We have that in order for us to say that our function is continuous at a point, now remember that's the domain, that means that as the limit of that function exists, all right? So that means this limit exists, which we already know is almost impossible for us to show, right? It's so hard for us to show limits exist, but to be continuous at a point means that the limit must exist and it must be equal to the function's value there. So that means approaching that point from every possible path, not only are we approaching the same place, when we get to there, that there's not an empty space there or an asymptote or something, it's filled in. So it's kind of like our sheet that's waving around in the wind. We can draw it without picking up our pencil. It's the same sort of thing. There's no little hole in the top of the surface or something. Now, it's so hard for us to show limits exist that what we wind up doing right now is we just give you a bunch of theorems. And so the mathematicians have already done the hard work for us, all right? And there's some very, very good results that we have that we're just going to just take on faith, okay? And my math majors can go prove this later on in their theorem proving courses. But these are all true, okay? So this tells us that all polynomial functions f of x, y are continuous on R2. So that means if your function contains just powers of x and y combined together with addition and subtraction. So I'm talking about functions that look like this. Maybe it's like f of xy equals, I don't know, x cubed y plus 3xy squared plus x minus y to the fourth. That's considered to be a polynomial function of two variables, because all the terms in this expression have powers of x and y, and those powers on the x and y are non-negative integers. So the powers are either 0, 1, 2, 3, 4, 5, 6, right? You never have negative powers, you never have square roots or anything like that. Every polynomial that you ever could think of in your life that is a function of two variables are continuous everywhere. And that just means that the sheet that's floating, right, because these are surfaces, whatever that sheet is that's floating around, there's no holes, okay? There's no breaks, there's no gaps, there's no jumps. It's just a nice continuous surface. All polynomials, all right? Now, rational functions are a little different, because now what a rational function is a polynomial over a polynomial. So that would be something like, I'm going to make this one a little easier, something like x squared plus y over y plus x squared. That's a polynomial function of two variables. I mean, sorry, rational function of two variables, because you have a polynomial divided by a polynomial. Those are also nice and continuous, and you can draw them without picking up your pencil, but there's a catch. Only on their implied domains. So if there's a point that you cannot plug into the function, like for example, look at this one. Do you all agree that I cannot plug in 0, 0? I cannot plug in x0, y0. But that's not in the domain of the function. This is saying as long as the point that you're plugging in is in the domain, then you are continuous at that point. That means if you look around, you're standing on the surface and you look around a little bit to your left, like a little bit in every direction, right? You're just sitting there looking around. There's like a little patch of surface all the way around you. All right, and then the last thing says, if you ever take two continuous functions and compose them, right? That means you take composition of two continuous functions, that you will still have a continuous function on its implied domain. Don't worry so much about that one right now. All right. Now we're done. All right, so that's it for 11.2. You should be able to do all those problems now. All right, now, I'll be honest, everything we've done up to this point with functions of two variables really is not that important, all right? Limits, we know they're hard to do, right? Continuity is hard to do because it requires limits, but the theorem tells us, you know what, when it comes to polynomial functions, rational functions, don't worry about continuity except on the implied domains. So now we move on. Here's where things get very important, and this is going to follow us the rest of the class. So what in your Cal 1 class, what was the order of things? You did limit, you did continuity, and then came limit,
Derivative?
the derivative, right? The derivative. So it's time for the derivative now. What is the derivative of a function of several variables? What is it, right? So 11.3 is what's called partial derivatives. And I don't want you to look at the word partial as meaning like we're not going to do like we're not going to cover this completely, okay? Like the word partial here doesn't mean like we're trimming it back for any reason. It's just there is something later on in math called the total derivative of something. You have a total derivative, and so this is not quite that. This is what we call a partial derivative. So the name is kind of hard to understand why you would call it partial, because you haven't seen total yet, right? Okay, so what is a partial derivative? So we know that in Cal 1, we talked about derivatives, right? And it was a very basic geometric idea. If we have some function, which is the blue curve, and we say, what is the derivative at some point? All the derivative represents is a number, which is the slope of the tangent line at that point, right? So you go to some point, some x value, let's see here. I know that's kind of hard to see, but You know, I'm at about 3 here, just about at 3. So the derivative of this function at 3 is about negative 8.68. So you got a negative slope, right? That's what Cal 1 was about, right? The derivative, slope of the tangent line. That's all it is. So for us, the problem that we have, or the issue we have, is that we have functions of 2 variables, which creates surfaces, right? And when you talk about a surface, is it even possible to talk about a tangent line? So I'm going to show you a surface now. Oh, I accidentally left my code open. Oops, let me close that. That's distracting. Okay, there we go. All right, so what you see here is a surface. It's actually the surface sine of x minus y plus cosine of x. This is a function of 2 variables, and it creates a surface, right? This nice sheet floating around here. It's not really floating, right? It's frozen, but okay. All right, so we've got this sheet here, and we can basically go to any point we want on this sheet. We can move around. Let me just move this point around somewhere. I'll move it over here now. And now we're down here, kind of in this bottom corner down here. But I can pretty much go to any place I want on this sheet. I'm just changing what value I'm plugging in for x and y. And I've got a point. So what is the, I guess, awkwardness of talking about a tangent line? What's awkward about it?
We only know how to take the derivative in respect to one variable at the moment.
What do you mean?
Well,
don't-
we know how to take the derivative of a function at y. One sec, I gotta figure out how to word this. We know how to take the derivative of something in respect to x so far, if that makes sense. We've
Yeah,
never
so
learned how to take it in respect to anything else.
Yeah, okay. I mean, I agree with that. We only know what it means to take a derivative with respect to x. So we only know how to calculate the rate at which y changes if we're given a little change in x, how much y changes. That's what the first derivative is, right? You have some function, you know, we have a graph here. We go to some point A, we go here, and then what we're trying to do, that slope of that tangent line, right, is dy dx. That's the notation for it. That's the same as f prime of x. That's basically how much y changes with respect to x. So it's a little rise over run, right? It's a little rise over run. So I agree with you. We only know how to do it with respect to x. I'm trying to get you to think about this geometrically, though. What's the problem with this? What's that?
If you take a line as the derivative, it ignores all the other ways that point can slope.
Okay, yeah. So, you know, with a 2-dimensional graph, and I put a point on there, there's really only one line that we can draw that's tangent to the curve, right? I mean, there's only one tangent line because there's only really like, I mean, it's actually 2 dimensions, but yeah, it's 2-dimensional. So, but there's no other way that we can go. Like if you're on that point, right? If you're standing here, if you're standing at that point, then you can either go to the left, which would make you go up a little bit, or you could go to the right, which would make you go down a little bit, right? And so the slope represents that rate of change in either direction, right? In one direction will be a little bit like if you went to the left, it would be like you go up, and if you go to the right, it'd be down. But if you're a point on a surface, like a tangent line, which way does it point, right? Like you could go, if you were on this point right here, you could walk in any direction, couldn't you? You could really walk in any direction. So here's how we do it, all right? Here's how we're going to kind of define a way of talking about the derivative, all right? You'll understand the problem, or like the challenge here is that it's not easy to just define a single line, boom, we're done. So what we're going to do instead is we're going to define 2 lines, 2 different ones, 2 different tangent lines. And those 2 tangent lines should help us come up with a tangent plane instead of a tangent line. But I'm getting ahead of myself. Let me just show you how we're going to do this. What we're going to do is we're going to fix we're going to just say, hey, look, right now this function has two variables in it, but we're just going to fix y. We're going to just hold y as a constant. So do y'all remember what this looks like? I feel like calling on somebody, but I don't want to get anyone mad right now. So I'll just ask for a volunteer. Can somebody tell me what y equals 3 looks like right here in this space?
A line, just a vertical or horizontal line. My brain's not working all that well.
I think it's
Okay.
a plane at the y equals 3.
Oh, that's right.
Yeah, so it would include the line, it would include a line, but it's actually the entire plane, right? Where all the y values are 3. And the plane that we would have would be parallel to the which plane? Y equals 3 would be a plane that's parallel to which?
To the z plane,
Z
to the
and
zx plane.
the ZX plane. Now I have it here for us. Okay, I was just trying to make sure I have the ability here to fix the plane. Here it comes. So I'm fixing the y value. Boom, there it is. Okay. Now, do you all see that that plane actually intersects our surface? Right, it intersects our surface. And if you look at it this way, isn't this intersection just a curve? Right? It's just a curve, almost like a Cal-1 curve, especially if we kind of turn and look at it from this direction. Like imagine looking at it from the side this way. Now, it's complicated to look at it this way. So what I've done is I've made this so I can actually pull the surface out and hide it from you so that you can just see the plane and just see the intersection curve without the surface in the way. And do y'all see that if we look at it this way, we're back in Cal-1? And all we're trying to do is figure out what the slope of that little line is right there. You with me? So if we take a function of several variables, in this case 2 variables, and we hold one of the variables constant, like y equals 3 or y equals 5 or whatever, then what it will do is it will create a 2-dimensional curve that we can find the derivative of. Similarly, let me go back to our original view here. And I will also point out that I held y constant, right? I held it constant, but I could have held it constant anywhere. Like I could have decided to hold it constant back here. And obviously that's changing that slope, isn't it? Y'all see that by changing the y, it changes the curve. So we would have a different tangent line depending on where we were. Right? Okay. So that's what would happen if we fix our y. Well, let's do something different. Instead of fixing our y, I don't like where this point wound up. Hold on. Okay, I want you to be able to see the point. There we go. So instead of holding the y and having a plane that's parallel to the xz axis, why don't we hold the x instead? Let's fix the x. If we fix the x, now our plane is parallel to the yz axis. And if we turn and kind of look at it from this perspective and get the surface out of here so it's not bothering us, then now we have a curve, a different curve in like a 2-dimensional space, and we should be able to find the slope of that tangent line. And do y'all remember that in order to define a plane, you just need what? What do you need to define a plane?
A point and a normal vector.
Point and a normal vector, right? Okay, so if we had, do we have a point that would be a, do we have some, let me bring that other one in here. This was the other plane and we had a partial, we had our derivative there. Do y'all see that the red and the black tangent lines, do you see that those create a plane? Right? And so those 2 lines, the red one and the black one, you could look at those as being vectors on the plane. And if we were to cross them, we would get a normal, wouldn't we? And so there is, and we have a point, the point where they intersect right here. That point right there is a point on the plane. And then we would have 2 like direction vectors that we cross and get a normal. And now you have the equation of a plane. So we actually have a way now we're going to have to go through the formal process of it, but we're going to have a way of finding a tangent plane. And that's the big, like, end of story, like final thing we want to arrive at, is that if you're given a function of two variables, you don't have a tangent line that you're interested in, you have a tangent plane that you're interested in. All right. Okay, cool. I hope that that all makes sense geometrically. Yes. You understand? Everyone understands what fixing, holding y constant, right, means you have a plane that intersects in one way. If you hold x constant, you got a different plane that intersects the other way. So those planes are, you know, orthogonal to one another.
Can we
Right.
fix the z?
Well, you don't fix z. Now that's a great, I was wondering if anyone was going to ask that. You don't fix z, and the reason you don't fix z is because this is a function of x and y. So our domain is on the ground, right? So if you fix z, yes, you could come up, boy, I don't have this prepared to do that. So I'd have to talk you through what it would look like. But imagine trying to cut through this with a plane that's parallel to the XY plane, so to the ground. If I had a plane that cut through here, it would probably like hit here and go around, but it would also hit here somewhere and go around. And so if we looked at it from the top, it wouldn't be a function of anything because it would fail like a vertical line test. But that's okay, because all we need are two tangents, not, you know, as long as we have two tangents, then we're in business.
Okay, thank you.
Okay, good question. All right, so let's get to actually doing something with this. All right. So the key point, all right, in order to find the derivative, this is the key idea. In order to find the derivative at some point, we will need to hold either the x or the y constant. Okay, you have to hold one of them constant to talk about the slope of a tangent line. So if we are given some function z equals f of x, y, if we hold the y constant, then we will call this the partial derivative with respect to x. So the function has two variables in it, x and y. If you hold y constant, then it's a partial derivative with respect to x. And the notation we use for it is this notation right here. It's the f. So we don't do this anymore. Like, that seems like that. Remember, that's what the prime meant the derivative back in Cal 1. But see, the problem is here, I need to somehow tell you which variable I'm holding constant and which one I'm actually letting be the variable. And so here, this means we're letting x be the variable and we're holding the y to be constant. So x is the variable, y is constant. So new notation, right? That's new notation for us. Now we have the other case where we would have the same function of x and y. We hold the x constant, and in that case, we call it the partial derivative with respect to y, because this time they switch places. Ah, shit, sorry. So here, this time y is the variable, and then x is constant. So here's some practice for you. Now, I'm going to just go refill my drink real quick. I haven't even done one of these. I just want to see what you do. All right. So see if you can try and calculate these two things, right? This first one, you're going to treat x like a variable. You're going to hold y constant and try and take the derivative. I just want to see what y'all do. I'll be right back. All right. Does anybody want to kind of tell me what they're thinking here on this?
I got A.
You got A? What'd you got?
Yeah.
What was your, like, can you help talk about what you did?
Well, since you have to keep y constant, I was thinking how normal derivatives, it has d squared y over d of x, and x is the one that changes. So I just acted like y was a constant. Like I acted like y cubed was the same as 10. If I took the derivative of 10 with respect to x, it's just 0. So y
Okay,
cubed
yeah,
is 0.
exactly. Okay. So everywhere you saw Y, you almost like imagined it was just a number.
Yeah.
Okay, that's critical. All right. So let's do this. First thing I'm gonna do, I'm not gonna answer part A or B yet. What I'm gonna do first is I'm going to do part A by first finding what is the partial derivative of this with respect to X. In other words, what happens when I take derivative of this and treat all the Y's as if they were just numbers? So like, who said that? As well? Did I say your name right?
Yes, as well.
Okay. As well said, okay, so basically we're just treating this like a number. The derivative of a number is 0. Okay, great. I agree. Okay, plus now the derivative of 2x. Well, x is a variable, right? So we're going to treat it like we did in Cal 1. The derivative of 2x would just be 2, right? All right. Now plus, now we run into an issue. We have x squared times y to the 5th. But y to the 5th is just some number, right? Just some number. So I almost like to envision that this is something like, I don't know, 7x squared, where the y to the 5th is like the constant, right? So what would you do if you took derivative of 7x squared? Just bring the 2 out front, right? Multiply it times 7, you get 14x. We're gonna do the same thing here. We're gonna bring the 2 out and multiply it times the constant, which is y to the 5th, right? So we would get, I'm going to write it this way, 2x, and I'm just going to leave the y to the 5th there. Y'all see that this constant is like the 7 is here. And I just didn't multiply 2 times that because I don't know what y is. So are there questions on that? Sure. I see like squinted eyes.
So
Plus-
why was the y cubed affected, but not the y to the 5th?
Good question, because there was no x attached to it. There was no x attached to it. So it'd be like the derivative of a constant by itself. The derivative of any constant by itself is always 0. But if it's attached to a function of x, then it just comes for the ride when you take the derivative. That makes sense?
Yeah, I think I got it.
Okay. All right, so that is the derivative of f. Let me just clean it up. That is a derivative of f with respect to x. There it is. Now, to answer the first question, part A, we want to know what the derivative of f with respect to x is at the point 2, 1, which means that now I can replace all the x's with 2's and all the y's with 1's. And this should give you 2 plus 4, right? Just 6. It's a number. We're basically taking this surface, we're cutting it with a plane. By the way, what's the equation of the plane we're using? Because we're holding y constant in part A. What's the y value we're holding constant? Y is what? Y is equal to what?
1.
1, because look at the y value, it's 1. Okay, so we're cutting that surface with a plane, y equals 1, and we're looking at that curve, and we're going to the x value of 2, and we're trying to figure out the slope of the tangent line. So back on this picture, just kind of reiterate what I'm talking about here. Now, this is not the function, so don't think that I'm actually showing you. I don't think I have that function here. No, but I do it. Nah, I won't do that. So what we did is we basically fixed our y value, and it created a curve. And then we looked at that curve from the side, we took out the surface, and now we went to an x value of 2. And we found that the slope of that line was 6. That's what we just did. Now, for a different surface, but that's the idea. All right. Now we need part B. So for part B, the difference in part B is now we're going to be taking the derivative with respect to y, which means we need to hold x constant, which means as we take the derivative, we want to treat all the x's as if they're just numbers. So the partial of f with respect to y is, okay, so let me see. I haven't called on some people in a while. Let's see. Fabiola, you're here, and I haven't called on you in a while. So what do you think?
It starts off with 3y squared.
3y squared. So Fabiola is saying, look, y is now our variable, so I'm going to take derivative of it the way I did back in Cal 1. It's just 3y squared. Good. Okay, plus derivative of 2x.
Would it just be 2x?
So
Or
x is a number, right? Okay, so just give me a number. Just make up a number.
1,
Okay, 2 times 1 is,
2.
now take its derivative.
Okay, so then 0.
0, right? So we have to see that 2x is just a number. So when you take its derivative, you get 0. Good. Okay, plus, we're going to keep going, Fabiola. So remember, x squared is just a number now, right? But it's attached to y to the 5th. So what would that derivative be?
5. Could it just be 5x squared? Y raised to the 4th?
Perfect. Everyone see that? So just ignoring the x squared, letting it come for the ride, taking derivative of y to the 5th, the 5 comes out, we reduce the power by 1. That's it. And then finally, plus derivative of 10, which is still 0. Okay, derivative of constant will always be 0 until the day we die. So we don't ever have to worry about that changing. So there's the partial of f with respect to y. Okay, now moving on. Let's see, Terrence. It's been a while, Terrence.
Yep.
Okay, so let's see. Can you do this for us? Partial with respect to y of 2, 1. So what are we doing here?
Just subbing in
Mhm.
2 for x and 1 for
Yep.
y, right?
That's it. Yeah.
I got 23.
23. I trust you. Anybody else get that?
Yeah, I got that.
Okay, good. So it seems like here what we've done is we've taken the surface, right? And we took that surface, and this time, instead of cutting it with the plane that way, we cut it with the plane this way. And we looked at it from the side, and we took out the function, and we fixed, this time we fixed our x to be 2, didn't we? And we're letting our x was fixed to be 2, but now we're looking, this is the y-axis now. And we're letting our y be 1, and we're going up there, and we're getting a slope of 23. So this is obviously not the picture, because slope of 23 means really steep, right? Really, really steep. I can remember being a student in Cal 3. I think I've told you all this. I can remember the room. I can remember everything about that class. And I can remember my poor professor, Dr. Arias. I couldn't remember his name earlier this semester, I think, when I was talking about him. Dr. Arias, he couldn't draw three-dimensional space for his life. And it was so hard to visualize what a partial derivative was, because he couldn't do this. Like, you know, I mean, no, I don't blame him. I couldn't do it either if I had to draw it. So it's really nice that we have technology now, because we can really kind of visually see what's going on, right? Hopefully that all makes sense. All right, we're gonna move on.
So
Yeah.
if you were to could you just, because it kind of gives you the plane that you're going to work on, could you just plug the value that you're making constant from the point?
For what? To do what?
Like on the f of x, y, or the one we just did,
Mhm.
could you just plug in the point before you did the derivative and then take the derivative of what you get?
Oh, I see.
Like just
I
take
think I know what you're saying. I think what you're saying is like when we're doing this, since we're holding y constant, right? We're going to hold y to be 1. Just replace all these with 1s before we do the derivative,
yeah,
and then do the derivative, and then let x go to 2.
yeah.
The answer is yes, but we want to be able to take the partial derivative at an arbitrary point. And that's what this is. This is the partial derivative at an arbitrary point. So let's say we needed to know the partial derivative of a function at, maybe we needed to know the partial of f with respect to x at 6 different points. Then you wouldn't want to do it and do that, what you were suggesting, 6 times. Instead, what you would want is a master formula, and then you just plug in the values 6 times into this. So it's just more efficient, that's all. Good question. You could do it, but it's just more work later.
Is the sums, once we got the sum, is that the magnitude of the tangent?
No, so one thing we have to keep in mind is that these are slopes of lines, right? Slopes of lines. That's all they are.
Oh, okay.
They're not vectors. They're not points, right? They're just a slope. So we still need to figure out how we're going to turn these into vectors and how we're going to do like cross product and get a normal. And it's going to turn out that it's going to be so simple. It's going to be, you're going to be like, wow, I can't believe it's that easy to do that. But for now, just keep in mind that those are just slopes of lines, right? That's all they are.
Okay.
Okay. All right. So now we move on to a harder example. Because we have sine of xy over x squared plus y squared. And so as we take derivatives here, we're going to need to be thinking about which rule? Sine of
The quotient rule.
quotient rule and
The chain rule?
chain rule, right? Okay, so I'm going to go through this first one. Let's see how this goes. Part A. I'd like to take the partial of f with respect to x of x at xy of the function. All right, so here we go. Everywhere I look, y is a constant. That's what I'm thinking. Y is just a constant. All right, so I'm taking derivative of sine of something. So I know that derivative of sine of something is always cosine of that something, right? So that doesn't do anything other than make a cosine appear out in front of this, right? So I've taken care of derivative of sine of this. Now I have to multiply, that's what chain rule says, multiply now by the derivative of what's in here, right? So now I have to look in here and take derivative. But that's quotient rule. So the quotient rule says that I have to take derivative of the top, multiply it by the bottom, and then subtract the derivative of the bottom, multiplied by the top, and then all of that over the bottom squared. So y'all remember that from Cal 1 and Cal 2 enough? So here's the way I'm going to write it. I'm going to write a big old fraction over here. I know that the bottom is just going to be x plus y squared. X squared plus y squared squared, sorry. Okay, because quotient rule is always going to spit out the denominator squared. It's the top part that I have to figure out. So the way that I teach the quotient rule in Cal 1 might be different than the way you're taught. Okay, the way I teach it is that quotient rule always starts out by taking derivative of the top first. So, Jorge, is Jorge here?
Yes.
Yes, okay, Jorge, you're up. Give me the derivative of the top with respect to x.
It's going to be y times x squared plus y squared minus...
Okay, hold on, slow down. You're correct, but you're going a little quick. So the derivative of the top, Jorge, with respect to x, you said is just what?
Y.
Y. Okay, so everyone, derivative of this with respect to x is just y. Because y is like a constant, right? So it's like, this may as well say 10x. And so the derivative of 10x would just be 10. Good. Then you said what?
Times x squared plus y squared.
Okay, so that's the bottom, right? So we have derivative of the top times the bottom, and then minus, you want to keep going?
Yes.
Go ahead.
2x times xy.
Times xy. So the 2x was Jorge taking the derivative of the bottom with respect to x. So derivative of x squared is 2x plus derivative of y squared was 0 because y is a constant. But then quotient rule says you have to then multiply by the top, which is xy. So there it is. Perfect. Good job. Now all I'm going to do is clean it up. Anyone have a question over any part of that? Let's see, this becomes x squared y plus y cubed minus 2x squared y all over x squared plus y squared squared. And I can actually put these two together, right? This one and this one go together because they're like terms. So the numerator really just turns into y cubed minus x squared y squared. That's what the numerator is. Is that all right? And that's what they wanted, right? They're not telling us to plug in a specific point. They just want the general derivative. That's it. No questions? Let's do the partial of f with respect to y. Donald here? Where's my participant list? Do we have Donald in the house? I don't see Donald. How about Juan? I don't see Juan. Maribel. Maribel? I see Maribel's here. She's usually real quiet. Maribel? Maribel? No? Habi?
Yes.
All right. Good, because you've looked like you're having a little bit of an issue with this, so this will be good. All right, we want the partial of this with respect to y. So let's see if you can take me through this.
Okay, so the first term would be the same, right? It'd be cosine
Of everything, right? Just rewrite it. There you go. Done. Boom, boom, boom. Okay, now quotient again.
Okay, so it's the derivative of the top.
With respect to y, which means
So
you
it'd be
treat x like constant. So you're saying it would just be x, yes?
times x squared plus y squared.
Good. Then minus.
Is it 2y?
Yep. Then times the top, right?
Yeah, xy.
That's y. There you go. And then everything just bottom squared. That's it. That makes sense, Abi?
Yeah, it's just my derivative skills are a little rusty, but the concept makes sense.
Okay. And now we could clean this up too, but I'm not going to. All right. All right, good. So you'll get more practice with this in the homework, obviously. There will be more problems. Now we need to talk a little bit about notation, because there's a lot of little things with notation we need to be clear on. So if we're given that z is some function of two variables, x and y, then the following are equivalent. So anytime you see in math, we write TFAE, the following are equivalent. You see this a lot. So that's what it means. The following are equal. So all of these notations mean exactly the same thing. So this meant what we were just doing, right? This means you're gonna hold y constant and treat x like a variable. Another way you could write that is just the f with an x below it. That would mean the same thing. So this is, I'll show you what this is kind of like, what this is like in the Cal 1 sense. In the Cal 1 sense, this is basically f prime of x. That's the notation we have, but now this is the new notation for it. Or sometimes in Cal 1, you wouldn't even write that, you would write just like f prime. That's what f prime looks like now. Then this is new. We also said like df dx, or sometimes we'd say dy dx. Those are these two notations. Now what we do is we don't use d, okay? It's d, but it's this weird sort of cursive weird d, all right? It's not your standard like d from the alphabet. It's just like curled d. And that's what we use whenever we're talking about partial derivatives. So this is saying we are going to take the partial derivative of the function f and then with respect to x. So instead of df dx, it's the partial of f with respect to x. Or you could say the partial of z with respect to x. See, z is the dependent variable. Or you could do something like this. Now this notation in Cal 1 was this, d dx of the function. That's notation you learned in Cal 1. So that would be like, you know how you saw this in Cal 1, like take the derivative of sine of x. So this means take the derivative with respect to x of sine of x. That's what it was in Cal 1. Now we put a little partial over partial x, and then we put the function here. The next three notations, we do not have equivalents of in Cal 1. These are new. So if you write f with the number 1 below it, it means to take the partial derivative with respect to x. How are you going to know that I'm talking about x? Why does 1 tell you that you're taking derivative with respect to x? Why do you think?
It's the first variable in the set.
Exactly. In the ordered pair that we have here, we have x and then we have y, right? So the inputs to this function are x and then y. And so since x is the first variable, we are taking the derivative, the partial derivative with respect to the first variable. So in this case, x. Or you could write capital D with the subscript 1 of f. That would also mean the partial derivative with respect to x. Or you could write capital D with the actual x with the f. So there's all these different notations. They all mean the same thing.
Why?
Why?
Yeah.
Yeah.
I
Well,
imagine the
Why do we have all these notations?
well, all of this is because now I don't remember if I've told you all this. There were two men that developed calculus historically.
Right.
There's Newton and Leibniz. And when they developed calculus, they had their own notations. So Newton had his own notation because they didn't even know that each other was doing what, it's amazing because they both developed calculus about the same time in history. And so they each had their own way of doing it because no one had ever done calculus. They were making it up, right? So they were using their own notations for things. Leibniz used this notation, or I should say this notation. So this notation, all of these are just to handle like, it's like a Leibniz notation with higher dimensional functions. And then all the other ones are more like Newton's notation. Now we need them though. We have to have them because right now we're dealing with functions of 2 variables, but I told you already, we could have function of 5 variables, 6 variables. So let's say I had a function of 6 variables and I wanted you to take the partial derivative and I wanted you to hold all the variables constant except for the third one. Then you would do like D3F there. That would take the derivative of that function, treating the third one as a variable, and all other variables would be held constant. So it's a convenient notation. To us right now, it looks like, why did we do this to ourselves? But okay. Well, we also have to know notation for taking second derivatives, right? Just like, you know, in Cal 1, we had f prime was the first derivative, f double prime was the second derivative, f triple prime was the third. But how do we do higher derivatives with functions of two variables? So if you weren't already happy with the notation, now you're going to be even more happy, right? So check this out. What does this mean? Well, that means you're going to take the function f, and you're going to take the partial of it with respect to x. That makes sense? It's in parentheses. And then after you do that, you're going to take the partial again with respect to x. So you go partial with respect to x, then partial with respect to x again. Another notation is fxx. And that is read left to right. So that means you do with respect to x first, then with respect to x, x again. Or you could do f11. That's not f11. That's f11, which would mean partial with respect to the first variable, partial with respect to first variable. Or this notation, partial with respect to x of the partial of f with respect to x. Or this one, or this one. If you want to do the partial with respect to y twice, these are the notations. And then these two are the ones you have to pay attention to, I think, the most, because they're a little tricky. Look at this one. This one says you take the partial of f with respect to x first, then with respect to y. The notation here, you go x first, then y, or the first variable, then the second, or with respect to x, then y, or here, the way it's read is x, it's read right to left instead of left to right. It's confusing. This is confusing. Here it's left to right. Here it's right to left. Yeah, it sucks. That's the way it is. Same thing with that one. And of course, we could keep going with this, right? Like you could have f. So this would mean you take the function, whatever it is, you take the partial with respect to x first. Then you take that answer, take that partial with respect to y, then you take that answer, do it with respect to x, and then you take that answer and do it with respect to x again. Find all second partials. All right, let's talk about what all the second partials are, and then I think I'm going to do one, and then I'm going to let you do the next three. So what are all the different partials we could have here? Second partials. So we could have fxx, we could have fyy, we could have fxy, we could have fyx. There's no other second partials. So let's do the first one. Okay, so for the first one, what I'm going to do is first let me find the partial with respect to x. So to do that, I'm treating what like a constant?
Y.
Y. Okay, so it'll be derivative of x squared is 2x. Okay, derivative of 4y to the fifth is 0 because y is a constant, right? So this is all a constant, derivative of that 0. Over here, I take derivative, y is a constant, so it's just going to sit here, nothing's going to happen to it. And this, I take derivative of x cubed, so 3 comes out, so minus 30 x squared y squared. Y'all see that? Then I'm going to do the partial with respect to x of that. So I go again. Derivative of 2x is just 2. And then same thing as before, the y squared is just going to come for the ride here. And when it comes for the ride, I get, let's see, 2 comes out, so negative 60 x to the first power y squared. There we go. So that's the answer to the first one. Now let me give you some time and see if you can get the rest of these. And why don't I give you like, I don't know, 6 minutes, see how far you get in 6 minutes. Would you all like me to like start working them out and not say anything, just work them out so you can look up and see, or want me to wait?
You can wait.
I had heard what you said as well, but there was like 3 or 4 people that nodded their head yes when I asked it originally. So that's why I put it up there.
It's okay. I understand.
Yeah, those are the 4 answers, everyone. Take a moment to look at them and ask me, if you have any questions, let me know.
Is that just coincidental that fxy and fyx are the same answer?
I was about to ask you the same thing.
I'm going to say it's not coincidental.
Okay. So what Benjamin's seeing and wondering is whether or not the fact that those 2 wind up being the same is always true or just a coincidence. If it's always true, then what Benjamin's asking is it safe for us to say that these 2 will always give us the same answer? And I'll answer that question in just a moment. Just want to make sure nobody has any questions about the arithmetic here. Everyone good? You'll get better at this. You'll get faster with it. You just got to practice. Okay, I'm going to move on. Can I clear the screen, or you want me to leave it there? Clear, okay? Okay, here we go. All right. Clairaut's theorem. Given a function of 2 variables, if f is defined on a disk D that contains the point x naught, y naught, and if the partial of f with respect to x, then y, and the partial of f with respect to y, then x, are both continuous on that disk D, then they will always be the same at that point. So the answer to your question, Benjamin, is yes, kind of. We have to have something be true. We have to have that when you take these partials, that when you look at those partials, that they are continuous on some little region near the point you're interested in. So like when we go back and look at this, that problem, I erased them all. But when we look at those, our derivatives, go back and look at what you just did. When you looked at the partial of f with respect to x and then with y, with respect to y then x, both of those answers were polynomials, weren't they? And polynomials are continuous everywhere. That was a theorem I gave you earlier today. So that satisfies the theorem. we have continuous derivatives. And therefore, we should always expect to see those be equal. If for some reason our derivatives aren't continuous, then it's possible that they will not be equal. All right. Okay, now, how much time? We got 7 minutes. So where are we headed with this? Where are we headed? All right, so we know from Cal 1 that we had a function, right? And the first derivative told us the slope of the tangent line, didn't it? And what that helped us do in Cal 1 was it helped us find these highest and lowest points on our graph. Because whenever we were at a highest point, we would have like the derivative be 0, right? The derivative would be 0 there. And then here, the derivative would also be 0. And there were also some times on our graph, oh shit. There were times on our graph when we would have, you could have something like this. This would be a local minimum. And here the derivative is not 0. The derivative does not exist. So what we learned in Cal 1 is that the derivative, the first derivative could be used to find critical numbers, critical points, which helped us find local max and local mins, all right? And then what did the second derivative give us in Cal 1? What did the second derivative have to do with?
Concavity.
Concavity, right? So just like, you know, the first derivative being positive told us that our function goes up. The first derivative being negative told us that our function goes down. And then the first derivative being 0 told us, you know, you might, maybe you have a max or a min there, right? That's basically what the first derivative was all about. The second derivative being positive told us that our original function looked like a smile, concave up. If the second derivative was negative, it told us our original function was concave down. And if our second derivative was 0, then we call that an inflection point. That ring a bell? So here in this 3-dimensional space, the first derivatives are going to help us figure out that tangent plane, okay? The second derivative is going to have to do with concavity also, but in a slightly different manner. So I want you to look at something. This might help you see it. Sorry if y'all can hear my dogs. Someone just rang the doorbell. Hold on. They respond to yelling. All right, so I want us to take a look at this function right here. Yeah. Look at this one. Okay, y'all see that? Do y'all see that we have like a maximum here? That max point. And if we were to cut it, if we were to cut this, maybe, you know what, maybe I can get that point. Let me clear this out. Maybe I can get that point up there. Let me get that point up here. Ooh, yeah, this is gonna work out good. Okay. Do you see that at this point? Let me pull the surface out a little bit so we can see it a little better. Okay, do y'all see that at that maximum? Do you see that the curve that we have where it intersects, do y'all see it's concave down? And then if I slice it the other way, like this, do y'all see that that's also concave down? So it's kind of like if our second derivative in both directions are concave down, it looks like we're probably talking about a maximum point. And if both of our second derivatives are concave up, then we're probably talking about a minimum point. But it's also possible that we have like concave down in one direction and then concave up in the other, and I'll show you that. Here's an example of that. Oh, this perfect. I wasn't even planning on it being this perfect. So look at that one. Now let me bring the surface in here so you can see it. And let me take these out of here. Okay, you see this weird surface here? We have happening here in one direction, we've got concave up, second derivative would be positive, and in the other direction, concave down. And that is not a maximum or a minimum, is it? That's actually called a saddle point, and I think I referred to this earlier in the semester. So the whole point of what I'm trying to get at is that the first derivative is going to be helpful in us determining where these things happen, just like in Cal 1. The first derivative helped us figure out where we might have maxes and mins. And then the second derivative can help us determine whether or not those are in fact maxes or mins. So it's similar to Cal 1. It's not exactly the same, but you know, it's kind of, it all has the same spirit, okay? It's not something different. It's still in the spirit of concavity and then up and down for the first derivative. All right. Let me see what else I had here. Okay, so I only have 1 minute. So this last one is just an exercise, and I believe that's the same problem, isn't it? Yeah, it's the same problem. So I'll just show you one of these real quick in 30 seconds. For this one, we have to do partial respect to x, then y, then y, then x. So you move from left to right. Didn't we already do that? Okay, and what was that? I forgot. That was what, negative 60x?
Negative
X squared y.
X squared y, right? And now that is fxy. And now we would want to do it with respect to y again. So fxy, y. What would that be? So y is right there. So this is all a constant. So negative 60x squared. And then we do it one more time, but now with respect to x. And that would give us negative 120x. These are just higher order derivatives, okay? You could check this one yourself too. I won't do that.
Can I ask a quick question?
Yep.
The x and y's in our partial derivative notation, are they commutative? Like if I took the derivative of yx, would that imply the same thing as the derivative of xy?
That's a wonderful question. Well, here's what I can tell you is that it's commutative in this theorem tells us it's commutative sometimes, right? So if you do x then y, it's the same as doing y then x, right? But I think what you're asking is that more generally, can you do that with something like this? So could you, let me say like for this one, could you do, is that the same as, right? Like f, maybe x, x, y? Am I correct to?
Yes.
Is that what you're asking?
Yes.
Well, I think I'll leave that as an open question.
Dang it.
Well, I mean, but in the spirit of maybe you can answer that question yourself.
I know.
Because in math, here's what makes mathematics difficult. If you have an idea, like you have a conjecture right now, Daniel. Your conjecture is that this operation of differentiation is commutative in this sense, right?
Mm-hmm.
So the thing that sucks about math is that to prove that, you have to actually have a formal proof that shows it's always true for all functions. But to prove it's not true means all you have to do is find one example where it doesn't work, right?
Mm-hmm.
So maybe you can come up with they call it a counterexample, which would be an example of one that does not do what you think it might do. And then you're done. And then you've answered your own question. And I'll tell you right now, do you want to know the answer? Or do you want to?
Well, I could spend all week trying to find a single example, but if a single example doesn't exist, then I'm just going to be wasting a week of my life.
Okay.
A lot of what mathematicians do is waste weeks of their lives proving something to be true.
But most of them aren't in college with a job.
I would say it's beyond weeks. I'd say years, sometimes half of their lifetime.
In that specific one, it works.
Yeah, on this one. So here, let me give you, I'm going to come up with a counterexample. All right.
Okay.
Let me see. And if y'all have to go, you go. That's fine. Let me say x, y, y. Okay, I'm going to come up with a function first. So let me tell you what my thinking is here. I'm gonna want this to make everything go to 0. Okay. So I'm gonna try and make it so that when I do this, I get 0, but then when I switch it around and do it this way, I don't want it to go to 0. So maybe I'll start here.
That one's yxx.
What's that?
Would that be yxx? to
No,
make
we're
it
generating a new
sec-
example.
No, but I'm saying the f of the bottom
Well,
one.
I think Daniel's asking, can you commute these? So can you swap the order of these any way you want and it still be true? So
Oh,
I
okay.
just need 2 y's and 1 x in any order. Is that correct, Daniel?
That is absolutely correct.
Okay, so let me do this. I'm just gonna go for this shot in the dark here. XY cubed. Okay, so if I do this with respect to x, right? First, I treat y like a constant. So what do I get? Y cubed,
Yeah.
agreed? Sorry, that's just the first one. So x, that's gonna be y cubed. And then if I do that with respect to y, I get 3y squared. If I do that with respect to y again, I get 6y, yeah?
Mhm.
Okay, so if I do this, you know what, it's probably gonna work for polynomials.
Yeah, I was thinking it might. I was thinking if I were to find it an example,
Yeah.
it'd have to be trigonomic.
Yeah, I'm pretty sure trig will do it. Yeah, because if we do it with y, first time we do y, I get 3y squared x, and then do it again, we get 6y x, and then with respect to x, we get 6y.
So maybe we can make a simple conjecture that the derivative is commutative for polynomials. And then bada bing, bada boom. That makes life very easy. You could just knock out all variables in one case, all the variables in another case, and you're done.
Yeah,
Easy clap.
yeah, that would be a good. Yeah, it would be, you would have to prove it though. That would be the hard part.
I don't think I've ever heard easy clap in a math class.
So I'm a New Yorker. I love stupid sayings. Me and my friends talk in the most stupidest language there is. You'll never hear it anywhere else. It's amazing.
Hey, that's good. That's like we say y'all all the time here down in Texas.
Yes, I had to learn to force myself to say that one for my job.
Yeah. Let me think about it, Daniel. You work on what you got to work on. I'll think about it. Maybe there's some way of, I know there's a counterexample because I know it doesn't work in general. That I can
I could
guarantee
believe it. I just was curious. I figured it would be an interesting idea. And if it is, and it does hold true, like we see so far for kind of polynomials, you can just knock out all of the variables. You know, what is the 5th derivative of in respect to all x and then the 5th derivative in respect to all y or whatever, and just run through it
Well,
all.
now, but what you said was change the well, what you said is commute, right? So
Well,
commute
yes.
means, that means this would also be something I'd have to look at, right?
Yes.
Okay, so if I do that, does it work? So with respect to y, we get 3xy squared, and with respect to x, we get 3y squared and then 6y. So it works there also.
So then I can rearrange it. So that way I can knock out all of my y's first since they seem the most tedious, knock out the x, and boom. And then that's the example we got up there, our second example.
Yeah. Yeah, let me think about it. I think the polynomial condition will have to be there, but it would be a nice, interesting result if that were the case.
Be very clean, a very helpful type of math trick.
Yeah.
In my opinion, you know,
Yeah, I
maybe
agree.
not everyone's.
In Clairaut's theorem though, right, you need the continuity. And
Yes,
so you're never going to have continuity be bad if you start with a polynomial. Because every time you take derivative of a polynomial, you're going to get a polynomial. So I think in that, Clairaut's theorem is basically saying exactly what you're saying, but only for 2 derivatives. The question is, can this be extended to, multiple derivatives, like 3 or 4 or 5, and truly commuting? This is just, when you have 2, there's only one way to commute, right? But if you have 3, there's, several ways, and 4 and so on and so forth.
what level of math would I probably need to follow along with the proof of Clairaut's theorem if I were to try and Google it? Pure mathematics, linear algebra, which one would I have to suffer through?
I don't think that there's, I think all you would need to know is how to prove something. So what you would have to do is I don't think that there's any class. The only thing you'd have to know is how we prove something. So there would be maybe some theorem proving course sort of ideas, but I mean, basically it would just go like this, let f of xy be equal to a general polynomial function, right? So a general polynomial function would look like this. I'll do it this way: a sub m x to the m y to the m plus a sub m minus 1 x to the m minus 1 y to the m minus 1 plus dot 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 all the way till I get down to a sub 1 x y. Oh wait, no, I can't do that. This would have to be n.
Yeah, I was wondering about that for a hot
This
minute.
would have to be n because they don't have to be the same power as n minus 1. Yeah, okay, hold on. And then this would be like that. And so all the way down to some constant. And then let's change this to a k. So this would be k minus 1. We'd have k terms, right? We'd have k terms.
Mhm.
And then the degree of, by the way, the degree of this polynomial would be these two added together. So this would be an m plus n degree is what we call this, the highest two powers added together. So then all you'd have to do is start taking derivatives. So you would say like fx would be, and so what would fx be? It would be m a sub k x to the m minus 1 y to the n plus a sub k minus 1 times m minus 1. You see what I'm doing? Just power rule on all my.
I feel like we're gonna have to need some type of mathematical induction to prove this.
Maybe, but you got to start somewhere, right?
Yes.
So then you go with that, and then you say, now let me do, fxx and see what that looks like. And yeah, I mean, this doesn't seem like a straightforward proof.
Yeah, because where we're going right now, we can just take as many derivatives as we want since we've generalized it to m and n. So we're
Okay.
definitely gonna need some we're definitely probably going to need some induction here. Or
Yeah.
something along those lines. I'll look up the formal proof
Yeah,
and see if I could tweak it to work for polynomial functions. Or at least support my conjecture of polynomial functions being commutative in their derivatives.
yeah.
Is
partial
it like
derivatives.
sequencing?
What's that?
Like sequencing of the derivatives, what you were trying to do earlier to see if f sub xyx is equal to f sub yxy. Is that like the sequencing has to be the same or similar?
Yeah. So the question is, does it matter what order you do this? Is this equal to this? And is that equal to, every possible way you could order those for polynomials? Now we have to, start polynomials. But the problem, and this is what Daniel's talking about using induction, is that this is, you could do it for just 3 derivatives pretty easily. But what Daniel's saying is, well, what if we do this? It doesn't matter how many times we do that. It could be like x, y, 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 x, x, y, right? Is that equal to x, y, and the same number of x's and same number of y's? And that would be basically, there's no limit on how far you could go with that. Like you could have this where you do the derivative, 8 times, 10 times, 100, 1,000. And that's where something like induction, which Daniel, you said the word induction. So I'm assuming you've seen proofs by induction before.
Actually, I haven't. I just know about them and I know roughly how they work. I'm a math nerd. I plan to minor in it for fun.
Yeah.
Has nothing to do with my major.
Yeah, no, induction is a very powerful tool that we use to prove things that cannot be proven easily any other way. I still don't even know if this would set up for induction. I don't know. Something tells me here, something like this would be easier if it was done using something like talking about, and this is where you would have to have a more formal math thing, is where you talk about the space of all continuous functions of two variables. So you talk about the space of all functions that are continuous, that are polynomials. And then you talk about the operator. So the differential operator, okay, what the partial derivative means, right? And oops, partial. And then talking about the properties of taking a certain space and what happens to that space under this transformation, which is more abstract.
Sounds
but
like
would
abstract
probably-
algebra.
Yeah, it would be like an abstract algebra thing, exactly, where you're talking about, you start with a certain space, then you do something to it, then what do you get at the end? Because the derivative is unique in the sense that, we talk about functions in algebra and stuff, and those take numbers in and those spit numbers out basically, and those are functions, right? But when you take functions in and spit out new functions, right, something different, I'll call it f tilde, then the operation that takes a function in and spits a function out, these are called operators. Okay, it's not a function, it's an operator. And the derivative is what we call a differential operator. So this would be, like you said, more of an abstract algebra thing where you're saying what happens when you take a certain functional space, the space of all polynomial functions of two variables, and send them through the differential operator. What can you tell me about that space? And are things, is the operation of differentiation commutative within that space? And that is definitely an abstract algebra thing.
So we've made some progress. I now have an idea of what field to look in to figure out a proof for this,
Yeah,
or at least a supportive type of. So I don't know. I got a life to live. I'm not going to try and prove it.
yeah, that's true. See, this would have been brute force. That's more of a brute force attack,
Yeah.
which sometimes works, but in this case, I don't think it would. Induction may, but I see some problems with induction.
I guess
Because
induction was a shot in the dark.
Yeah, no, but I mean, it could, but I don't see it straight away that would be any easier than the brute force.
There does
Yeah.
seem to be, just from problems I was trying to do while listening to this,
Mhm.
there seems to be some kind of pattern to it.
Yes, there seems to be some
Like-
type of pattern, which is why like I'm calling it a conjecture, and
Yeah,
like it's got some like support to it, but we have no way of at the moment proving it. It kind of just looks to be true.
Well,
Yeah.
I tried a trigonometric, and I tried
Ooh, how'd it
A-
work with the trigonometric?
if it worked perfectly fine if only one of them is being trigonometric, if only one of them is like inside the thing. I
So,
didn't
like
try
f
with
of sine
both,
of
but I
y-
have a
sorry, x.
feeling. Yeah, I did y squared sine of x.
yeah, that
Okay.
won't work, right? This
That
won't
did
work.
work.
This did work?
Yes.
Oh, that one did work. Okay, you're saying, but if you do like that or something, then you're in trouble.
Yeah, then it
Put
stops
more than one
making
variable
sense.
inside. Yeah. So I mean, this is actually the thing that attracts, well, I don't know if it attracts people to math or not, or it forces them away from it. Like math at a pure level, okay? At the pure mathematician level, this is a problem that you want to know, right? So it's like I said, it's very easy to prove something's wrong. It's very hard to prove something's right. So, for mathematicians who are doing like their dissertations and, working on their PhDs and things like that, it's all about first having a question, right? And the question has to be something that nobody's asked yet, or at least nobody has an answer to yet. And then what you have to do is come up with a proof of your conjecture. So the first thing you usually do is try and find a counterexample. So you sit there and you try and figure out if you can prove yourself wrong. So that way you're not wasting your life doing it, right? And then you go, if you can't prove yourself wrong, then you say, okay, let me go try and make a proof. And that's the hard part, is doing the proof. So It's in math, in the math world, it's called original thought. Okay, that's what you're looking for. Original thought. You know, because math is thousands of years old, and what you're trying to do is think of something nobody's thought of and prove something no one's proven.
A lot of
And-
people to try to create
Yeah.
a new idea out of.
Yeah. So
Hey man,
it-
just solve the Riemann's hypothesis and
yeah,
just bada bing, bada boom, there's your dissertation.
yeah. I
Or
think-
find Graham's number.
There you go.
Yeah. Yeah, so I mean, it's yeah, I'll mess with this if I have some time. I have some grading to get caught up on, but this is, I think definitely that the proof of that would be outside the scope of this class, but it's definitely within the world of a mathematician to look at.
As far as I could tell with all of the ones I did, it works with pretty much any simple version of something. Like it worked with simple versions of the inverse functions and radical functions.
So non-polynomials, it was working with non-polynomials?
It seems to be as long as the y and x are part of different like pieces of the function, it will always work.
Yeah.
Hmm.
Which
Sounds
that would make sense. That would make some sense. Only because if they're separated, you know, if they're separated, then when you're holding something constant, right? Like when you hold this constant, if that y wasn't here, if you hold the y constant, then the impact of this on this, it just comes for the ride because it's a constant. It doesn't
Until it's its
disappear.
turn to be messed
Yeah.
with.
until it's
I don't know
Now-
if I'm wording this right, but it kind of sounds like to me that it will work if if X and Y are found in the same space. If I'm wording that right, like how Y is currently found in sign and outside of sign. So
No,
it's in
that's
the
where
sinusoidal
that there
space
is-
and the non-sinusoidal
That
space.
one there doesn't work.
Exactly. So they're not in the same space. I don't know if I'm wording that right. So it's not going to work. It's just another conjecture to throw onto the conjecture. So now we
Yeah, I
got a
guess-
lot, but
if you would, so yeah, again, going down like the math way of thinking of this is, let's say you were able to prove that it's true for all polynomials, right?
Okay.
Then you'd start asking, okay, what else is it true for? And then what you do is you try and come up with like the minimum requirements, the absolutely minimum requirements in order for that to be true. And so like that theorem that I gave you, Clairaut's theorem, these are the minimum conditions. For these two to be equal, the minimum conditions are that you have the derivatives of these are continuous. That's it. That's all you need. And then you can be guaranteed this is true. What makes me weary about this is just that, like in general, what makes me weary is that I know it's not true in general. We know that already because we've
got an
that example there doesn't work, right? So trying to find the classification that would make it work, that might be hard. Yeah. I'll think about it. I've got to go. I've got to be somewhere at 3:30. So
All right.
I've got to leave. But good question. We'll leave it as open and maybe get back to it later.
Have a good one, Professor.
Okay, everyone have a good one.
Have a good day.